This time we're going to take a look at three different molecules. We're going to look at their angles that they normally have and how they change when you have some different situations. So the first one we're going to look at is the element H2O. So H2O, in the H2O molecule, in this case I'm going to draw a little Lewis dot structure to the right here. So we have our oxygen, which is the red one right here, and we have our two hydrogens. Now normally I draw the hydrogens at the top. This time I'm drawing them at the bottom because at the top on this one are two sets of unpaired electrons. And remember, this is supposed to be three-dimensional, so you can think of those dots as maybe coming towards you and going into the screen as well. And they're creating the molecular geometry of a tetrahedral. Now that's the major geometry here because it's got an AX2 E2 and it adds up to 4. But because it has an E2, we also say that it's got a subcategory, and the subcategory is bent. And anytime a molecule has any sort of geometry, we can put an angle to it. So tetrahedrals are normally 109.5, and I say normally because there's an angle of 109.5 between all of the molecules. But there really isn't that angle right here because of the unpaired electrons. Those unpaired electrons are very close to oxygen, and because of the negative nature of those electrons, they're pushing away the electron cloud of the hydrogens. So instead of 109.5, it's more like 104.5. So the angle between the hydrogens is smaller than normal. So this is the unusual aspect because of those unpaired electrons. When we take a look at this next one, we have the molecule, say, NH3, otherwise known as ammonia. There's our N, our H's are the white spheres, and therefore the thing that we're missing here is a set of unpaired electrons at the top there. So if we were to draw a Lewis dot structure, it would look something like this. We would have an H out here, an H over here, and maybe an H going back a little bit like that. And again, it has a tetrahedral, major category, and tetrahedral adds up to 4. It's got an AX of 3 and E of 1 adding up to 4. But because of those unpaired electrons at the top, they change that 109.5 degree angle that normally you would see between those outermost atoms. And what it does is these unpaired electrons right at the top here, they push on the hydrogen, so instead of 109.5, it's more like 107, I think, between all of the hydrogens. So the difference between there is 107 degrees and 107 degrees between those hydrogens right there. So again, the situation we have here is normally 109.5 because of those unpaired electrons at the top of the tetrahedral. Pushing down on those hydrogens, 107 is the new angle. This next one is different. This one is trigonal planar, but I'm going to give you a carbon, an oxygen, and 2 chlorine. And this is called phosgene. Phosgene is a kind of a dangerous gas that was used during the wars, actually. And what we're going to do here is we're going to put a double bonded O at the top, say, and a single bonded chlorine there and a single bonded chlorine there. And because of that double bonded O, it's actually closer to the carbon than the chlorines are, so it pushes down on the chlorines. Now, normally, this would have an AX of 3, doesn't have any unpaired electrons on the carbon, and therefore, since it's AX3E0, it would be trigonal planar, and the angle difference would be 120. But because of the double bonded O, it changes this so it's less than 120 degrees, and I think the real angle is about 111 111 degrees, if I'm not mistaken, or maybe even 112. Just that situations like this, unpaired electrons, in this case the double bond, it's going to be less than the normal angle between those molecules. So that's what I'm looking for you to kind of get from all of this. Hope that helps.